Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. So today, me, Ahmad Afif Arifudin, with my group, which consists of Yusuf Arfan and Akmal Najmi, will be presenting about relating gravitational acceleration G on the surface of the Earth with universal gravitational constant. So let's go.
According to Newton's second law of motion, F equals to ma. Force equals to mass of object times acceleration. However, when involving gravitational acceleration, we substitute the A for G, resulting in F equals to mg. That is the first equation. The second equation is from Newton's universal law of gravitation. F equals to gmm over r squared. If we observe correctly, both equations are for F, gravitational force, so we can equate them actually, meaning that mg equals to gmm over r squared. As we can see, there is a common factor on both sides of the equation, being m, lowercase m, which represents the mass of object. So we can cancel each other on both sides, leaving us with a new formula, which is G equals to gm over r squared. Okay, as we know, the further we are from the Earth, the lower the gravitational acceleration. So here is a graph between gravitational acceleration and the radius of orbit. The first part of the graph, we can see that the value of G is directly proportional to R. Okay, the first part of the graph represents when we are beneath the surface of the Earth. So the closer we are to the surface of the Earth, the greater our gravitational acceleration. So the second part of the graph represents the radius of orbit when it is above the surface of the Earth. So the further you are from the surface of the Earth, the lower your gravitational acceleration would be, because the further you are, the lower the gravitational force exerted upon you. Here is a diagram of the Earth. From here to here, this is the radius of the Earth. If we extend that 2 times its length, it will become 2r, meaning it is twice the length of radius of Earth. So on, 3r, meaning it is 3 times the radius of Earth. 4r, 4 times. And finally 5r, meaning that it is 5 times the exact radius of Earth. Okay, let us look at a few questions regarding gravitational acceleration. The first question: mass of Earth is 5.97 times 10 to the power of 24 kilogram, and the radius of Earth is 6.37 times 10 to the power of 6 meters. Calculate the gravitational acceleration on the surface of the Earth. From the question, we can identify the values of m, capital M, r, and g. The question asks for gravitational acceleration, meaning that it is asking for the value of the lowercase g. So, with the information given, we can identify the formula we need to use, which is G equals to gm over r squared. Note that r is for radius of orbit, but since the question asks for gravitational acceleration on the surface of the Earth, the radius of orbit is the same as the radius of the Earth. So the next step is we simply substitute the values. G is 6.67 times 10 to the power of negative 11 times 5.97 times 10 to the power of 24 over 6.37 times 10 to the power of 6 squared. We will get the answer of 9.81 meter per second per second. Right, for the second question, a radar imaging satellite orbits around the Earth at a height of 480 kilometers. What is the value of gravitational acceleration at the position of the satellite? Given G, M, and R. Alright, the question asks for gravitational acceleration, as we know is the lowercase g. The question gives the universal gravitational constant, G, mass of Earth, M, and capital R, which is the radius of Earth. So the formula we need to use is G equals to Gm over R squared. However, in the formula, the lowercase r represents the radius of orbit, whereas it is given here that the capital R, the value of capital R, is actually the radius of Earth. Now, as we know, the radius of orbit is from the center of the Earth to the center of the object. So, we need to add the height of the object as well as the radius of the Earth, resulting in the new formula Gm over R plus H squared. Alright, then we substitute as usual. 6.67 times 10 to the power of negative 11 times 5.97 times 10 to the power of 24 over R, which is 6.37 times 10 to the power of 6 plus the height. Okay, note that the height is in kilometers. We must remember, whenever we are doing calculations, we must always use the SI unit. The SI unit of distance is meter. So what we do is we convert 480 kilometers, convert it to 480,000 meters. So instead of plus 480, we plus 480,000 squared. This will result in the answer 8.49 meter per second per second.
Earth satellite can provide information of atmospheric conditions and further help in study and forecast of weather. The Earth satellite in orbit can transmit and transfer the information across the Earth. Research in the field of medicine can be enhanced by obtaining results from zero gravity or weak gravity. Spaceship can use gravity of a planet to move forward like a catapult. This can save energy and move them further. Rocket can land on the surface of the planet safely if we know the gravitational acceleration of the planet. Space satellite can orbit the planet and provide information about the surface and the surrounding of the planet.
Breathing is related to air pressure and not gravity. Gravity affects blood flow to the lungs but does not change the size of the lungs. Density depends on mass and volume. The mass and volume do not change with gravity. Moving from the gravity of the Earth to the gravity of the Moon, one's weight may change, but the mass remains the same. Thus, density does not change with gravity. Gravity smaller than the gravity of the Earth can cause bone density to decrease because bones do not need to support the body against larger gravity. As a result, the bone become more fragile and easily broken, especially on the hips and spine. In microgravity, the output of the heart, that is the amount of blood pumped out of the heart, decreases. Blood circulation is lower and blood pressure is lower than on the Earth.